Okay. Welcome everybody to day 2, part 1 of our 5-axis post-processor course. So when we left off last time, we had just finished building a new version of the Generic Fanuc 5X mill post. We've decided we're going to start with a Cincinnati Gantry. So we're doing a Cincinnati Gantry 5-axis machine with an achromatic 950 control, and we just happened to pick a random, 5-axis Gantry style machine. And we started to look at the setup, and I created a real simple test, basically a cylinder. And we've got a 12-inch diameter arc, 6-inch radius. From that, I created the actual cylindrical surface. And what I did was to drive the tool path as a curved 5-axis. So we went in and did a curved 5-axis tool path. We picked a tool, I'm going to grab a 1/2-inch ball. Under cut pattern, the type of pattern that we're driving with curved 5-axis is a chain, and in this case it's going to be 3D curves. And I used the single method to grab that chain. Under tool axis control, we used surface, so the tool is going to try and stay normal to the surface as we go around the chain. And I pretty much just used the defaults. So I got this last time because I forgot to change a couple of things. Under cut pattern, we have normal to plane or normal to surface. We definitely want to stay normal to the surface. And then the maximum distance, I usually give it at least, a little bit of distance here. Because you can see in the picture, anything where, the curve is farther from the surface than whatever distance you put in here, you're not going to get any projection. We are going to tell it to leave a little bit of depth. So, where are we at here? Collision control, vector depth. In this case, we can either do tip control on the projected curve, or we can compensate to a set of surfaces. And this comp surface doesn't necessarily have to be the same as the drive surface. And that's one of the real kind of tricks and benefits of 5-axis, is being able to choose a cut pattern. And the cut pattern is, how does the tool motion move relative to whatever you're cutting, and have that be separated from the collision control. In other words, what are you compensating to? So with the collision control, we're compensating to something. With the cut pattern, we're telling Mastercam how do we want to move the tool. In this case, vector depth, I'm going to stay 50 thousandths up off of the curve. Make those changes, and when we backplot, you can see that the tool starts down here, wraps around, and then finishes up. So when we do a setup for any kind of 5-axis machine, it's really important that we pay attention to the kinematics of the machine itself. And kinematics is just a way to say, how do the linear and rotary axes move relative to each other, and what part of the machine is bolted to what? Because that will change how the machine behaves with the same toolpath. So we can take this toolpath, and it's a it's a really simple example. Let me do this actually. Let me let's do this. I'm gonna move this. I'm going to trim the surface down a little bit. I think it'll make it easier to see in the example. So when we look at this kind of raw motion, if we go into backplot and we turn on the display of the vectors, and then we start stepping through, this gives us the first position that we're going to see in the NC file. And what we end up having is the tip of the tool and then the center of the ball. And we also get the surface normal. And so here you can see we've approached the surface. We're at y minus 6.15. Z10, and this is all relative to our WCS origin. With the generic Fanuc 5x mill post, all of the code for 5-axis machining is always relative to the WCS origin. There is no option to offset the 5-axis vectors by the tool plane. For 3+2 machining, using the generic Fanuc 5x mill post, we have the ability to switch between using the WCS origin or using the tool plane origin. So that's something that's important to be aware of. So as we start to make our first rotation, so this is the first non-orthogonal tool vector. And what I mean by orthogonal is the tool itself is no longer aligned with the y-axis. It's slightly angled, and you can see that now. And so what we have here is the tip coordinates, which is the actual coordinates of the very tip of our tool. And then we have the center point of the ball end mill. And this distance and direction is represented mathematically by a vector. Now, a vector is really just a line. When we start talking about vectors, though, it's important to differentiate between a couple of things in terms of how we describe the motion. Right now, when we look here, this is a tool axis vector. In other words, the orientation of the tool is aligned so that these line endpoint coordinates, this tip here and this back end right here, represent the center line of the tool. This vector happens to be a vector length that is not 1. That's a little bit important because we have some math functions that use what's known as a unitized vector. And a unitized vector is a vector that has a vector length of exactly 1 unit. In inches, that means 1 inch long. In millimeters, that means 1 millimeter long. And when the 3D length of a vector is equal to 1 unit, it has some special mathematical properties. We can use it in some formulas to derive angles. And that's what we're doing mathematically inside the post. So we're doing a lot more than that, though, because not only do we need to know where the tool vector is, on the actual machine, we need to know what the pivot length of the tool is. What is the distance from the tip of the tool to the center of the rotary axis? And this will become a little easier to understand if we look at this tool path in the machine simulation module. You go ahead and save it. So with machine simulation, we can actually go and select any one of these sample machines. And it's not necessarily going to match our posted code output, because we can have a post that is set up differently from the way that this particular simulation interprets the generic code. But what we end up getting is at least a decent idea of, will the thing fit on my machine? What kind of motion is going to be generated? That type of stuff. So we're going to take a look at some examples here. So this is a vertical machine, table BC. That's how you break down that the wording that they've got here for the name. So vertical machining center, twin table, BC axis. If I go look at the 5-axis head, this is just a generic 5-axis head where the rotation's in the head, but there's no real machine loaded. Then we can see we've got a VMC table AB. So here's the similar configuration that we just saw, which was a BC, except this is an A and B. So this is like a Haas VFTR style machine, where you've got it's labeled A and B, but the actual alignment of the axes is A and C. You know, I don't know why Haas decided to name it AB no matter what. Now you can see we've got VMC head table AC. This is one of those mixed mode machines where you've got a table that holds the workpiece that spins, and then you've got, in this case, an A-axis that rotates this tool. Head table BC, very similar. It's just this one rotates about Y instead of X. Table BC, this one happens to be a Nutating. You can see it's a DMU. We got a Boston-matic, which is a head table BA. Herco, table AC. And pretty soon here, we're going to get down to what I'm looking for, which is a CA. So here's a VMC head CB. And VMC head CA. Really want what I want is the head AC. I'm not seeing the good one. Alright, we'll pick one of these heads. Oh, head CA. You know, it's got this laser thing, which has got this weird configuration. You know what? We're going to use it. So basically we're just loading this on a generic machine. One of the options that we have, let's see, fixture, we can tell it, you know, if we have fixtures, we can grab it from a level, which is nice. We can do selected elements. In this case, I'll do non-stock, and we'll do not use stock. And basically setting all this stuff up, and then we say simulate. So what we've got going on, the way this particular machine is built, this isn't a good one to use. So grab a different version. Current simulation is still discarding. Okay. What a nice gantry. I thought they had one. Oh, I'll just use the head CB. Let's see. Yeah, there are some options as well. You can see that it's putting the origin right here. There's an option in here, at least there was, to transform into WCS, which essentially allows you to take, it allows you to take whatever geometry you're driving and move it to another place on the machine. Let me see where this is at. Position. Translation in XYZ. And this is exactly what we got going on. So you can see it's automatically putting a translation of -9 in there. If I left it 0, it would be, you know, 10 inches up top, but the origin of the machine's at this back corner. So we're going to go like -30 in XY. And then because we're probably got it on some kind of riser or something like that, I'm going to put it up another 15 inches in Z. So now when we do that and we say simulate, this is what allows us to kind of shift it on the table. Oh. I think I did the wrong way. I think I should have done positive. So, gotta wait for it to discard. Do. Positive 30, and could have sworn -30 would do it in X. We'll see, I guess. Okay. So here we've moved the piece that we're machining But you can also see the way this machine is aligned. This is the x-axis, and you'll notice that in Mastercam, if we look from the top and we look at this back plot, we're approaching the tool along Y. So somebody's asking a question, do you have a file that we can open to follow along with us? No. I'd like you guys to pay attention to what I'm doing on the screen, and if you've got questions to ask, please do. But this isn't like I'm going to do one thing and I want you guys to click along and then I do something else and click along. It would just take too much time and we'd get bogged down. So by all means, if you've got questions about what I'm doing, please ask them. If you'd like to ask them in person, you can always let me know in the chat box and I can unmute you so you can ask the question. But there's a lot of stuff to go through. And so if I were to give you guys all the files and have everybody try to tag along with me, we'd get nothing done. Because every other person would be like, oh, hey, well, I just tried that and it didn't work. Well, it didn't work because you were trying to do something, but you weren't watching what I was doing. Sorry, I don't mean to get like snippy or anything, but it's just there's a lot of stuff to go through and really don't have time to walk anybody through stuff step by step. I'm hoping that by going through a bunch of stuff over and over and showing you how the post works, that it's going to lead to a good all-around understanding of the whole concept. So that's the way that we've got this class organized. When we look at this, so we've got our move list, which is essentially all the positions that we're going to. And if we go and click on machine, here we go, statistics. Because of the configuration of our machine, which is an A or a CB, not a CA, you can see that we automatically had to rotate the C-axis in order for our vector to line up with the part in Y. If we were designing for a BC machine, this is not the correct setup because we're starting along Y. So if we look at the machine itself, and we go to axis control, so here's the machine, here's the part that we've got, and here's the position of all these axes. So if I now take my C and go towards 0, which sometimes can be hard depending on what your travel limits are. So this unlimited travel is making it hard to just grab an easy position. So I'm going to exit. We have to wait for a second for it to catch up. And we're going to go change a few things. To wait for it to discard. Okay, so I'm going to go back into the configuration for the machine simulation. We're doing the Como, and so here's the machine itself. And now if we go to machine definition, right now it's set to detection mode auto detect full. If we now change that to manual mode, you can now see that this gives us the configuration for the components of the machine. So first axis vector shows the way, for the rotation, shows the way that it's pointing. And then we have min-max in degrees for the head. So if I make this positive 360, negative 360, with a C. I can also make this one and change the alignment so that it's an A axis, but the problem is that my STL files aren't aligned properly, so that's not really going to work. You can see that we do have plus or minus 100 degrees of travel. So now I'm going to go back in to simulate. Okay, here's our part sitting out in space. Here's our machine. What does the machine look like if we rotate to 0? Oh, it's supposed to... didn't reset. Okay, you know what? We're going to have to do a save as. So we set this up and we've configured our post as a gantry. And the machine definition that we've got is a BC. Now, if that really was our machine, if we did want to set up for a BC machine, we can use that as an example. But the other thing that we're going to need to do, if we're using that one as an example, is to rotate our geometry for our starting point. Our starting point right now is starting at Y, and it's on the Y negative side pointing towards Y positive. So looking again in the gantry, let's do this. Got our linear axes. We should be able to save this. Yeah, it used to let us save. We already have the machine tool simulation. It's in here somewhere. It used to let us save. I'm surprised it doesn't. Huh. guess we're not allowed to add our new ones anymore. That's interesting. So, yeah, we used to be able to build machines. Surprised that we can't anymore. Let me see if I say okay. Machine sim to do it. Oh, I got you. So, build all yours. So. Got it. Interesting. Okay. Huh. See, it still didn't change my. Yeah, Jeremy, if you've got a an AC, I'll certainly take it. Well, okay, so that's getting kind of away from what I was going to do here. Yeah, so this is BC. Okay. If we look at this on a BC machine, you can see what happens. We start at C minus 90, minus 90, and right here. And then as we start stepping through, a single step. Ugh. There we go. So as we look at the cutter going around the path, turn the path on here. Control progress report. Here we're seeing B and C angles. The B angle is staying locked at negative 90. The C axis is rotating as we're going around the part. So we started at negative 90 over here, and we've crossed over 0, and we've gone to positive 19. If I hit play again, pause it, now we're at C positive 90. We're going to get around to the back edge here, and we're going to be at C positive 180. And when we come all the way back around, we're going to wind up at C270. And that's because of the way that this machine is built kinematically. It is a BC machine. B meaning that this secondary axis rotates about the y-axis of the machine. And if we were going to set this up for a BC machine, well, first let's see what kind of machine it's set up for. So I'll save that. Okay, so we've posted out that file. And this is the code that we get. It is set up for a C and B. And as you can see, in the simulation we were getting C90, B negative 90, or B90. And here we're getting C180, B90. So we're getting C180 because the post thinks that in order to approach from this vector, we actually have to rotate around 180 degrees to get this position where our spindle is. And that has to do with how the post is currently set up. Now, it's important to know how is our machine configured in the real world. And that's the first thing that we got to do. First thing that we got to do is we have to go to our machine and we have to establish how are the rotary axes oriented, and you have to go into handle jog or MDI and you have to command some positions. So you have to rotate your you have to rotate your primary plus or minus and see which way does the machine rotate. You have to rotate your secondary plus or minus and you have to see which way it rotates. Once you know that, then setting up the post becomes a lot easier. So here we can see, all right, we got C180, B negative 90. What that means is that, and by the way, what I usually try to do with this test on a 5-axis machine, whether it's a Gantry or whether it's a Trunnion, I want to rotate the secondary axis 90 degrees. I want to approach the part and I want to cut a 360 degree cut. And you can see here we started at C180 and then we started going down. And we go down until we hit 0, which happens in between these two moves. And we just go negative. So now we're going negative 180. And Jeremy is exactly right. The code needs some X and Y move for head-head output. This is set up right now for a table-table machine. We can tell that just by looking at the code, because all we're doing is getting C-axis rotation, which would be fine on a Trunnion, but it's not cool on a Gantry, right? So we got to fix something. So I'm going to open up our 5-axis PDF file. So this post and PSB file is set up to support what is essentially 6 different machine types. There's really 3 machine types or 3 regular machines and 3 nutating machines with the same configuration. So it's either both rotaries are on the table and they move the part, or one rotary is on the table and one rotary is on the spindle, or both rotaries are on the spindle and only the tool moves. So with the head, the part stays stationary. These nutators are the same thing, only the rotary axes are not at 90 degrees to each other. So what's built into our post? We have intelligence that is built in to detect rotary limits and automatically retract and reposition the tool to continue the cut. We have the ability to define a safety box and make the tool move around that box whenever we do repositioning. And so that's doesn't matter if it's full 5-axis or if we're just doing a bunch of 3+2 moves, we can automatically get the tool to retract. Typically this is going to be for a head-to-head machine because we have a separate safe Z retract for table machines. We have the option to bias the starting angles at tool changes and or on the secondary axis. We can fan a cut with the rotary axis to prevent part gouging. So this is when the post detects that there is a lot of motion going on, so both rotary and linear, and if it's greater, if the move is greater than the tolerance you give it, the post will calculate intermediate tool axis vectors to give you smoother motion and prevent the part from gouging. We can support axis substitution and polar conversion, and it also has limited support for a right angle or compound angle head. Usually it's just right. The generic 5-axis posts are MP post processors that have part of their data encrypted using the MP bin utility. The encrypted post section is written to a file with a PSB extension. You must have both of the files to run the post. Both files can be renamed to produce new post processors. An MP bin will also allow you to rebin the post to protect portions of your customized code. So what that means is that you can take the existing PST and PSB file and you can take part of the code that you write into the PST and you can encrypt that, and MP will automatically add it to the existing PSB. So if you are, or if you want to write posts commercially, you have the ability to do that and protect your work. The encrypted source code for these posts is not being released to customers or dealers. Specific post sections can be exposed if required on a situational basis. Now, I'll give you guys a heads up. Not only does CNC software not release the full source code for their post, I've written a ton of 5-axis post processors over the years. I've written well over 100 of them, and not once did I ever need access to the PSB portion of the post. I have access to the PSB portion of the post. I'm telling you guys the God's honest truth. Like, I have the fully unencrypted post processor, and I still have never needed to edit anything in that PSB section. I found, I think, one bug over the years that I, reported to CNC software and they fixed, and that was like X4. So I'm telling you that if you understand the way that the post is structured, how it goes off and makes its calculations and when, and you know where and when to override the output, you can make it do whatever you want it to do. And you still don't need access to the encrypted math routines. There's no output from the PSB. all of the output occurs inside the PSD file. And for that reason, as long as you know how the NCI is processing, the sequence of events that are going on, and you know where to override, you have the ability to override just about everything that you could possibly need. So at some point I may just open up the unencrypted version, and we'll just go through some things real quick so you can see how much stuff is in there. And honestly, even if you did have access to it, there's so much stuff and it's so complicated that, I've spent a long time studying the code that's in there just so that I've got a better understanding of it. And it's just so complex, man, that you really, it doesn't, whether or not I have access to that section, I don't need to edit it. So other than, your own personal knowledge, having access to it doesn't really gain you all that much because there's so much stuff going on. It's spaghetti code. There's so many things that are tied in together. Even if you had access to it, there's not many people who can trace through all the different decisions that are being made and know, and need access to that, honestly. Oh. So, how do we configure a 5-axis post? First thing we have to do is we have to get the data. What is the axis layout on the machine? Where are the rotary axes when the machine is at the home position? How does the machine interpret the rotary data? So what does this line mean? How does the machine interpret the rotary data? What this means is, how does the machine move? In other words, if you command A15 and then you command A negative 15, which direction does it rotate? What are the rotary axis limits? All machines, when you buy 5-axis machines, will have this kind of data in the manual. So usually a PDF file that'll tell you, hey, this machine, C-axis is plus or minus 225 degrees, and A-axis is minus 45 plus 110. Okay, you need that data. You need to know how to define the part orientation in Mastercam. And really, there's a couple pieces to this. You need to know how to set up the actual parts that you're going to machine relative to the WCS origin. And you also need to do something like this, where we're testing that 5-axis output, and how do we orient it so that we can approach the part, cut a full 360-degree circle, and retract. And where's the start position on this test piece? So we need to know that. You need to determine which is the primary and which is the secondary axis. We'll talk a little bit about that. And then you need to configure the post. So, get the data. Obtain a picture or drawing with the machine at the home position. Have the axis address marked on the drawing. Show the signed axis movement with the limits. Here in this example, Z positive is going straight up. You can see that Y positive's to the back. X plus is going that way. And that is going to depend a lot of the times on whether the tool is moving or the part is moving as to which way the positive direction is. Here you can see we've got looks like a C axis, and they're showing the positive rotation direction that way. And then this is a B axis, which has got positive 30 or negative 30, B minus, and plus 106. So that's the configuration of this machine. When we start looking at the part orientation in Mastercam, how the part is placed relative to the Mastercam WCS is critical in producing the proper NC code. Parts are normally oriented to match the machine's zero state. Train your customer, and in this case the customer is who is ever setting up the part to be programmed. That may be you, or you may be setting up the post and then one of your coworkers is using it. But they need to be trained to always place the part drawing or the WCS with the orientation you have determined is needed to produce the proper code. Nutating machines always have the part oriented in top view. This post processor was really designed to use the system top WCS. In some cases, it is possible to program using the WCS in airplane coordinates. I would recommend, at least initially, when you set up and are testing the post, just start with something simple like this. I mean, I've got, a circle with a cylinder, and I've located it, at 0, 0 and put it up 10 inches in Z. I mean, it's real simple. You always want to start with something simple before you move to the complex. Determine which axes are the primary and secondary axis. The primary axis is the rotary axis that is rotated first to position a tool vector in the plane that is perpendicular to the secondary axis of rotation. Determine the primary and secondary axis by imposing the machine coordinate gnomon onto a simple part drawing in the proper orientation for the machine. So if we're looking at the coordinate system, you can see here that from the center, this is Z plus, this is Y plus, and to the right here is X plus. And we've got these kind of standard rotary axes shown here. We've got A rotating about X, we've got B rotating about Y, and we've got C rotating about Z. In this example that we show here, what we're trying to see is if we rotate the part on the platter, is this one, which one of these is the primary? Now, if we look through these couple of slides, it's talking about, okay, so if Y, B axis is the primary for the Z vector, okay, here's the Z vector up here, and we're rotating about B, so we rotate down to X minus here. Then, in order to get it on the other side, it says Z plus solves to C180 on the secondary. Assuming the YB axis is the primary for the Y plus vector, Y is infinite on the primary, and Y plus solves to C90 on the secondary. So basically what they're saying when you look at this is that the B axis in this configuration, and this, honestly, these couple of slides right here are like the most confusing slides in the deck. I've often kind of looked at this and said, man, there's got to be an easier way to explain this. What they're saying is that in order to get the proper position, it makes much more sense to make this platter the primary so that we can rotate it into position first, and then we make the B axis the secondary to rotate it into position. And this will make a little bit more sense, I think, with a practical example, which is why I'm kind of skipping ahead just a little bit so that we can get to that practical example. And this is where we talk about assuming the z-axis is the primary for the z plus vector. Z plus is infinite on the primary. Z plus solves to B90 this way on the secondary. For the y plus vector, y plus rotates C90 to the primary and then resolves to B180 on the secondary. So basically they're saying look at the two configurations and see which one makes sense to be called the primary and the secondary. My general rule when I'm looking at this, the primary is typically the rotary axis that has the most travel. If they have similar amounts of travel, then the primary is typically the one that is farthest from the machine base. So in the case of head-head, and we'll see some of that in a second here. Okay, so 5-axis configuration known cases. Anytime we have a Trunnion style machine like this, the primary axis is the rotary axis fixed to the machine tool. And the secondary axis is always the axis mounted on the primary with the head-head. So whichever one is closest to the spindle, closest to the tool, is the secondary. This is the secondary axis. It rotates this way. The primary is the closest one to the z-axis column. So this would be the c-axis, and this thing is either A or B, depending on how this headpiece is oriented when both rotaries are at 0. For a nutating machine, the primary axis is the rotary axis aligned to the z-axis of the WCS. And the secondary axis is always the nutated axis with nutating type machine tools. So here's one where the c-axis platter rotates about the spindle, and we've got a b-axis that's mounted at 45 degrees to the table. So there's a lot of stuff that we go through to talk about. Imagine the vector rotating and blah, blah, blah. I think when you see the practical example of setting it up, posting it, look at the code, change something, see how the code changes, it makes a lot more sense. And we'll get to that right at the next section here. So once we've kind of gotten the data about the machine that we're creating, now we go through and we set variables in the post. And that's what we're going to be doing here in just the next section of class. So we go through and first we set M-type. And M-type is basically a global variable. Numbers are 0 through 5. And this indicates the overall type of machine we've got. I guarantee if we go and we look at our post right now, M-type is set to 0. And that's why we are getting this output here. Okay? So we're coming up on first hour of class. So I'm going to go ahead and split the video now. We're going to take our mid-class break. And when we come back, we're going to go through and we're going to make our changes and start testing the post. In the meantime, if you guys have questions, as always, please put them in the chat box. And it's basically 35 after. We're going to come back here at 50 after the hour, so about 14 minutes from now.